We're continuing this series of lessons on stoichiometry. Today we're going to learn about percentage yield. The homework problem for last night was based on what you're doing for the lab. And the question is, if 2.50 grams of aqueous 2 lead nitrate reacts with 3.50 grams of aqueous potassium iodide, what mass of precipitate will be produced? And so what we're asking you for essentially is a theoretical yield. Precipitates are the solids you form, or when you write a balanced equation, when you break the products, the solid will be a precipitate if you're in an aqueous environment. So we're starting with lead 2 nitrate. So lead is Pb. Lead 2 means there's a positive 2 charge. Nitrate, one of the polyatomic ions you're supposed to memorize, is NO3, 1 negative. To charge balance lead and nitrate then, we're going to need 2 nitrates. Okay? It says in the problem it's aqueous, so you don't have to even worry about whether you are looking in the right place on the solubility rules or whether you've memorized them correctly or not, but all nitrates are always soluble. Now, let's see, the other one is potassium iodide. So potassium is K. Iodine, or iodide in this case, is capital I. Potassium is in column 1 of the periodic table, so it has a 1 plus charge, and iodide is in column 7A or column 17 of the periodic table. And when you have monoatomic ions of all of those elements in column 17 or 7A, and those are called halogens, those are -1, they have a -1 charge. So a 1 plus, a 1 negative, that's charge balanced already as written, and this is aqueous. Now, column 1 metal salts are always soluble. Okay, so any of the alkali metals that are bonded with anything else, okay, you're always able to dissolve those, and we call those aqueous if there's water around. Iodides are mostly soluble. There are some exceptions, but potassium is not one of them. Now, if we have 2 ionic compounds, and that's what we have. You know this is ionic because it's a polyatomic ion. That's your clue. You know this is ionic because it's a metal bonded with a nonmetal. If you're looking at the periodic table, everything on the left-hand side of the periodic table, from this stair step that runs right along here, everything over here is a metal, everything up here is a nonmetal. And so we have an ionic compound because the metal and the nonmetal bonded together. If you have 2 ionic compounds like this, your first prediction, your first guess, is that you're going to have a double replacement reaction. So the front part of this compound goes with the back of this. Now I'm not balancing the formulas yet, I'm just putting the 2 parts together. The front part of this compound goes with the back part of this one. And then we want to find out what the physical states are before we proceed forward, because if there's not a driving force, and what physical states you form over here, it will give you a driving force for this reaction, if there is a driving force. Of course, we know there is because it says there's going to be a precipitate. We just have to really figure out which one it is. So iodide compounds, we said, are mostly soluble. There are some exceptions. Lead is one of the exceptions. So this is going to be a solid, and that provides a driving force for this reaction. So the formation of a solid, the formation of water, or the formation of a gas are the 3 driving forces when you have a double replacement reaction. Nitrate compounds, we said, and column 1 or alkali metal salts are always going to be soluble, so this is aqueous. Potassium is 1 plus, nitrate's 1 negative, that's charge balance. Lead 2, and although the charge can change as you go from one side of the equation to the other, unless I give you a reason to know it's going to change, you can always assume, or should always assume, you have the same charge over here that you started with on this side. And this is lead 2, and iodine has a 1 negative charge. Lead 2 means it has a 2 plus charge. We need 2 iodines, or iodides, to charge balance that formula. So now this equation now is set up in terms of the formulas are balanced. What we have to do now is to balance the overall equation. Once you have the formulas balanced, you don't touch them. The only thing you use to balance an equation are coefficients, numbers you can put in front of these formulas that will change the number of the whole formula, the number of each formula unit. So we're going to make a list of all the elements we have in this equation. We have lead and nitrogen, oxygen, potassium, and iodide. We're going to make a kind of a grid here. One of the things that I've told you before is always save oxygen for last when you're balancing equations. That doesn't mean you have to list it last. It simply means that you are going to balance it last. First, we're going to count all the elements we have. We have one lead. We have two nitrogens, because we have two nitrates. There's two outside the parentheses, means we have two nitrates. Each nitrate has one nitrogen, so that means we have overall two nitrogens. We have overall 6 oxygens, 1 potassium, 1 iodide. On the right-hand side, we have 1 lead. We have 1 nitrogen. We have 3 oxygens. We have 1 potassium and 2 iodides. We want to save oxygen for last. We're going to start with nitrogen here just because it's near the top. Just doesn't matter really. To get 2 nitrogens on the right, we're going to put a coefficient 2 in front of this species. I left off the plus sign here. I need a plus sign between these two species. That's going to change on this side the number of potassiums and nitrogens and oxygens. So now we have 2 potassiums, we have 2 nitrogens, and we have 6 oxygens, and the equation's balanced. Alright, so we're starting with 2.50 grams of lead nitrate and 3.50 grams of potassium iodide. We're starting with 2.50 grams of aqueous lead nitrate and 3.50 grams of aqueous potassium iodide. It doesn't matter when you're figuring out what your limiting reactant is, which one of those two you start with. So I'm going to start with, just because I listed it first in the problem, 2.50 grams of lead 2 nitrate. We're going to have a molar mass to convert this into moles. So we're going to write this lead and nitrogen and oxygen. On the periodic table, we can see that lead has an atomic mass of 207.2. Nitrogen is 14.01. And oxygen is 16.00. We have 1 lead. We have 2 nitrogens in the formula, and we have 6 oxygens in the formula. So 207.2, and this would be 28.02, and 16 times 6. We did that yesterday. 96. Okay, and so when we add it all up, we get 2 and 2. What's the rest of it, guys? Y'all got it done already, right? 331. Okay. We have an empty slot in our column of addition. Empty slots to the right are what matters, not empty slots to the left, because that's going to determine what numbers we have to round off here. This is going to be grams of lead nitrate, lead 2 nitrate. And we're going to use an arrow, because only arrows will do, to show that we're rounding off this number. And we're always going to write that equals 1 mole of the same species. Alright, this is a tool that some of you may not even need, that is to write this equals 1 mole, but some people do. So just to make sure that everybody's getting it as firmly as I possibly can get you to get the idea, we're going to write this as an equality statement every time, just to emphasize that a conversion unit, now conversion unit is different from a conversion factor. A conversion factor means something you do just to convert from one thing to another. A conversion unit actually equals 1. Okay, the word unit implies the number 1, and so this is going to be a conversion unit because I got 2 things equal in a fraction. I want to put the grams of lead nitrate on the bottom here because it allows me to cancel the grams of lead nitrate on the top here. And the 1 mole goes to the top. And this is going to allow us to cancel out grams and lead nitrate, leaving us with moles. So we're now in Moleville. This is where we need to be to go from one species to another. So what we need now is a molar ratio. Molar ratios come from the coefficients in the balanced equation. We want to match the units and species we have in the top of this part of the problem with what we put on the bottom here. So we're going to want moles of lead-2 nitrate on the bottom here, and there's an implied 1 here. So 1 mole of lead-2 nitrate goes on the bottom, and then we want to put on the top what we're trying to find. Since right now we're trying to find the limiting reactant, we want to put the potassium iodide on the top. So it's 2 moles because I got a coefficient 2 here. 2 moles of potassium iodide. And now we need to have the molar mass of potassium iodide in order to calculate this. So here's a K and here's an I. Potassium on your periodic table is 39.10. Iodide is 126.90. We only have 1 of each, so I really don't have to do the multiplication over here. Just simply add these 2 together. You guys already have this done, right? What does this come out to be? 1 what? 66? 166. That is grams of potassium iodide, and I do want you to say that's equal to 1 mole of potassium iodide. Now, there were no empty slots to the right over here, so there was really no reason to do any rounding off here. We can simply write that. So we have an equality statement now to write the conversion unit we need. In this case, we want the moles on the bottom because we have moles on the top here. In order to cancel moles of potassium iodide and leave ourselves with grams, we've got to put the moles of potassium iodide from here on the bottom. All right, and I'm sure you guys already have all this worked out. Let me cancel all our units we have. Okay, so what answer did you guys get? Complete answer. Speak up, please. 26. Okay, and that's grams of potassium iodide. We want to round off. We have 3 digits here, 4 here, 5 there. We're only looking at the measured or calculated numbers, and this has the least digits, so we want our final answer to have that same number of digits. So we're going to undo everything after the first 3 digits. And draw an arrow because only arrows will do, and we get 2.51 grams of potassium iodide. And that's the point we're going to use to figure out whether we're going to have what our limiting reactant is. Well, since in the problem we've got 3.50 grams of aqueous potassium iodide, we've got more than enough. Okay, what this number is the amount, the mass of potassium iodide that's needed to completely react with all of this 2.50 grams of lead-2 nitrate. Since we have 3.50 grams of it, in reality, we've got way more than we need. That makes potassium iodide is the excess reactant. And lead-2 nitrate is the limiting reactant. You can symbolize that LR if you want to, and you can symbolize excess reactant as ER. Okay, not to be confused with the emergency room. When you're calculating the molar mass, you're only interested in the number of atoms in the formula itself, not the number that are in the total equation. Okay, so we're only interested in the number of potassiums and iodides that are in the formula, Ki. If there are any subscripts, that governs that, correct. Okay? You don't even consider the coefficient when you're figuring out molar mass, because the coefficient is taken care of when we do this molar ratio. You don't want to double up. That makes sense? All right? So if that's a mistake you made, good. We cleared it up now, hopefully, and we won't have that problem in the future. You must start with the limiting reactant to find the theoretical yield. We got 3.50 grams of potassium iodide. That's our starting amount, our actual amount we're starting with is that. And to convert this into moles, we're going to put the 166.00 grams of potassium iodide on the bottom, 1 mole. You don't have to do both, because once you find the limiting reactant, Maddie, it doesn't really matter. Okay, once you find it, you got it. You don't have to do it both ways. But it's a good check, I suppose. Now, we want to have moles of potassium iodide from the balanced equation on the bottom. We got 2 moles of potassium iodide, so that's going to go on the bottom this time. And then the 1 mole of lead nitrate from here goes on the top, because this time we're going from potassium iodide to lead 2 nitrate. And we've got 1 mole in this case, yes. Okay, so Maddie, since you did this, what mass did you get here? Since you did this, what mass did you get? What total mass?
I got 3.491566.
Okay, and that's grams of lead 2 nitrate.
I thought you said it was going to be.
Say what?
I thought you said it was going to be the same.
It'll give you the same answers. It don't give you the same numerical answer. It will tell you the same thing about excess and limiting reactants. All right, again, we've got 3 significant digits. So we've got 3.49 grams of lead nitrate, lead 2 nitrate. Okay. So now, in the problem you're given, we started out with 2.50 grams of lead 2 nitrate. So this is the amount of lead nitrate I need to completely react with 3.50 grams of potassium iodide. Okay, this is, I need more of this to completely react with potassium iodide than I actually have. I only have 2.50 grams of aqueous lead 2 nitrate. So I don't have enough of this. That makes this the limiting reactant. Which you can write as LR if you want to. And potassium iodide is the, you could say, excess reactant if you want to. Okay? Either way, you get the same answer to which one's the limiting reactant. What?
That's not the part where you're doing the theoretical.
Not yet. This is where we start. You got to go. No. One or the other is fine. Doesn't matter which one. Okay? But now that we know what the limiting reactant is, y'all guys have a question? There's a lot of talking going on. I'm wondering if y'all are just talking about something else, or if you're, if you have a concern about what we're doing here. Okay. So once we know the limiting reactant is lead 2 nitrate, then we can start with the given amount. Okay. Now look, guys. Sometimes students make this mistake. They'll look down here and they'll start with this amount. That's not the amount of lead 2 nitrate you start with to calculate your theoretical yield. You have to start with the given amount of lead 2 nitrate. Okay? And we have 2.50 grams of that. So now we're going to find the theoretical yield starting with that 2.50 grams of lead 2 nitrate.
So this is the final answer.
This is how we're going to get our final answer for this question. Okay? Now we've already started some of the math. We actually did the same math, the first part of this, here. Okay, to convert to moles, we're going to use this same conversion unit. The difference is when you get to this molar ratio. Okay, molar ratios come from the coefficients in the balanced equation. We want the moles of lead 2 nitrate. Because we have moles of lead 2 nitrate here on the top of this fraction, we want moles of lead 2 nitrate down here, and you get those. This conversion factor of a sort, this molar ratio, comes from the coefficients of the balanced equation. We have a coefficient of 1 here, and that can be one formula unit, or if you multiply everything in here, you could say it's moles. 1 mole of this, 2 moles of that, and so forth. And that's where we get this idea of doing moles. As long as you multiply by the same thing, the ratio remains accurate. So 1 mole of lead 2 nitrate. And then we're trying to find the solid, and that's the lead iodide. And we have only 1 mole of that. Okay, the thing that we have to do that we haven't done so far is to calculate the molar mass of lead iodide. We got 1 lead in the formula, 2 iodines in the formula, and we get 461. Actually, I should have a 0 here and round that off. We've got an empty slot there. So this is grams of lead iodide, and we're going to round that off to 1.110 after the decimal. And we're going to say that's equal to 1 mole of lead 2 iodide. Okay. Now we have an equality statement to build a conversion unit here. Since I have moles here, I want to have moles down here. That's this side of the equation here on the right. So we're going to put that 1 mole of lead 2 iodide on the bottom. And the 461.0 grams of lead 2 iodide on the top. And do the math. 2.50 times 461. Hit enter or equals, and then divide by 331.2. And I get 3.47. 3.47970. 531 on this calculator, and that's, didn't cancel everything out. Make sure I've got everything set up properly. Okay, round it off. Grams of lead 2 iodide, arrow, 3.48 grams of lead 2 iodide, okay, and that's the theoretical yield. The question says what mass of precipitate will be produced, and you have to balance the equation to figure out what the precipitate is. If we're in an aqueous environment means things dissolved in water. We're essentially in a liquid. And so a precipitate from a liquid is some kind of solid. Okay? So the only way to figure out what a precipitate is to balance the equation to figure out what your solid is. There are lots of ways to find this answer. Okay? Another way to find this answer is to do this calculation starting with lead nitrate, and then do the same calculation with this to find lead 2 iodide. Okay, so you do mass to mass starting with this to this, mass to mass starting with this and go to this, and the smaller answer is your theoretical yield. And here's another way. Okay, I can take this and find the actual number of moles of this, find the actual number of moles of that, and compare the molar ratio together, and see which one's the limiting bracket. Now, a lot of textbooks tell you to do it that way. Okay, I'm not, I try to find a way to do it that seems the simplest cognitively for high school students. This one seems the simplest to me. But some teachers will teach you to take with this and calculate this, start with this, calculate to this, and see which one's a smaller amount. That's your theoretical yield. Okay, it also will identify your limiting reactant, because the one that gives you the smaller final amount of lead 2 nitrate is your limiting reactant. Alright, so in the previous problem, we found that we had a theoretical yield of 3.48 grams of lead 2 iodide. And so what we've done is to say, okay, if this is how much we theoretically would have gotten, but we actually got something else, then what is the percentage yield is what we're looking for. Okay? Now, our actual yield, when you interpret the problem, you read the problem and interpret it, what you actually were able to get out of the lab, what you actually were able to collect and weigh at the end was 3 grams of lead-2 iodide. And so there's about half a gram there that's lost somewhere. All right, it may still be in the solution because not all of it precipitated. It may be trapped or on the sides of a beaker. Maybe, who knows? I mean, there's all kinds of lab procedures and things like that that might cause that to happen. But we just know that we don't actually have as much as we theoretically could have, okay? And you never have 100%. It is impossible to get 100% in any lab procedure I know of, okay? And so what we want to know is, well, just how efficient is this lab procedure? Or this precipitation reaction? Does it really precipitate everything? And so what we're going to do is calculate something called the percentage yield. And percentage yields are really easy. Percentage yield is actual yield over the theoretical yield. And all of that done first and then multiplied by 100 to get a percent. Okay? Does that make sense? So percentage yield is just the actual yield divided by the theoretical yield multiplied by 100. Now, I want to show you something about percentages. If we take this actual yield of 3 grams, and that's 3 grams of lead-2 iodide, we put it over 3.48 grams of lead-2 iodide, put it in parentheses, multiply by 100 to find our answer. If you follow the procedure I've taught you to follow, and you should, units are going to cancel. Okay? Percentages are always unitless answers. Percentages are always unitless answers. If you have a percentage and you weren't able to cancel the units, something's wrong. Okay? Just so you know. Now, having said that, let me clear up something just in case you read some food label somewhere where they violate this rule I just gave you. Because occasionally, in the food services industry, I have seen them divide mass by volume and call it a percent. That doesn't make sense mathematically. Okay? Doesn't make sense in any chemical process that I'm aware of. But sometimes they do it, okay? Just because they do it doesn't make it right. You got that? You with me? You understand? All right. So, if in chemistry, if you can't cancel the units out when you get a percent, something isn't right. That makes sense to you? You got that? Okay. So if we do this math then, 3.00 divided by 3.48, and then times 100, and I get 86.20689655%. Now, in this case, it's also true that our species is canceling. Anytime you do a theoretical yield, anytime you do a percentage yield, you should cancel out, you should be able to properly, if you set it up right, cancel out your species. If you don't, something's wrong. Okay? Having said that, there are some percentages where you don't cancel out the species. All right? But the percentage yields always have the species cancel out. So just kind of a check on yourself. Any kind of percentages you cancel the units. For percentage yields, you always also cancel out the species, okay? But there are some percentages like percent composition where you don't cancel out species. Now, we're going to round off here properly. 3 significant digits in both these numbers, so we want 3 in our final answer. Round it off. And the final answer is 86.2% yield in lead 2 iodide. Okay? And that's a complete answer to the question of what is the percentage yield. Anybody have any questions about that? So you know percentages. It's just a fraction, right? It's a part over whole times 100. Every percentage is always part over whole times 100. That's what a percentage is. Part over whole times 100. If you remember that, you should be able to figure out how to calculate any percentage you can think of. Okay? Part over whole times 100. Got that? All right. Let's give you a chance to work on another problem.